In this video, we're going to use the logarithmic functions to work with the exponential functions in a bit more detail. So the first thing we're going to do is try to solve some exponential equations that we couldn't solve before. So for instance, if I had the equation 3 to the 2x is equal to 4 to the x plus 1, I cannot write 3 and 4 in the same base. Because they're different. They're not powers of each other. So I can use logarithms to solve this. So if this number should be equal to that number, then the log of it should equal the log of the other one. Okay. So in particular, I'm going to use the ln, the natural log. Okay. But you could use log base 10. Okay. Anything that your calculator can handle. Is okay to use. So I prefer ln, okay, but you can do whatever. So we're going to take the natural log of both sides. Okay, so that's going to be ln of 3 to the 2x is equal to ln 4 to the x plus 1. Now the reason why we do this is because now the log rules tell us that we can pull these powers down to the front, right? So the powers are on the entire thing inside the log. So this is going to be 2x times ln 3 is equal to x plus 1 times ln 4. Okay, now ln 3 and ln 4, these are just numbers. Okay, so here I have a number times x plus 1, so we need to expand it in. Okay, so this is 2x ln 3 is equal to x ln 4 plus ln 4. Now we want to solve for x, so we want x's on the same side. So I'm going to subtract x ln 4 on both sides so that it goes away on this side. So I have 2x ln 3 minus x ln 4 is equal to ln 4. Now I can factor out the x on the left because there's x in both terms. So I get x times 2 ln 3 minus ln 4 is equal to ln 4. Okay, so if I divide by 2 ln 3 minus ln 4, I get x is ln 4 divided by 2 ln 3 minus ln 4. Now, because I picked ln to use, I can actually compute this number. I shouldn't put equals because it's approximately equal. So if we use our calculator, there's a button for natural log. So you would do natural log of 4 divided by, and then you should put brackets around this because you want to divide by all of that. If you do that, you should get approximately 1.710. Okay, so this is our exact value for x and an approximate value for x. That would solve that one. Okay, let's try one more. So here I have 5 times e to the 0.01x equals 9. Before I take the ln of both sides, so if I took the ln of both sides right now, I'd have ln of this thing. Okay, this is not a power to 5. So that means I wouldn't be able to drop it down. So what I want to do first is move the 5 over. So I'm going to divide both sides by 5. And that's going to give me e to the 0.01x equals 9 over 5. Okay, so it's smart to solve for the exponential before you take the log of both sides. Okay, so now I can take the ln of both sides. Okay, which then lets me bring the exponent down because it's only on the e. But actually, remember that ln is actually log base e, so the ln and the e actually cancel out, but I'm going to write it this way first because then it's going to be ln of e. Okay, ln of e, this is 1, okay, because it's base e. So e, what power do I need to raise e to get e? Well, that power is 1. Okay, so then I get 0.01x equals ln of 9 over 5. So that means that x is ln of 9 over 5 divided by 0.01. So that's our exact answer. If you want an approximate answer, you can use your calculator and you'll get 58.779. Okay, so you want to solve for the exponential and then take the log of both sides, whether it's log base 10 or log base e. I prefer log base e, but whatever your calculator can handle is fine. Now, the last thing that I wanted to talk about, now that we have access to the logs, is the derivative of a to the x. So I promised you that I would try to convince you of this one more. So we can actually figure out what this is using logarithms and the chain rule. Okay, so first, let's just think about a to the x. Okay, I can actually write this as e to the ln of a to the x. Because e and ln cancel out, this is just a to the x. Okay, why would I want to do that? Is because now I can bring the x down in this exponent. So this is actually e to the x times ln a. And ln a is a number. Okay, so this is just e to some number times x. Okay, so for any a, it's just a number. And we know how to take the derivative of e. Okay, and now we with the chain rule, we know how to take the derivative of this. So the derivative with respect to x of a to the x is going to be equal to the derivative of e to the ln a times x. Okay, so we can use the chain rule. So maybe if you want to write this out explicitly, this would be our inside function. Okay, so u would be ln of a times x, and then my y would be e to the u. Okay, so then dy by du is e to the u, and du by dx is just ln a, because I have a number times x. So if it was 2x, the derivative's 2. If it's 3x, the derivative's 3. Ln a is just a number. Okay, so if it's a number times x, it's just a number. So that means that my derivative is dy by du, but evaluated at u. So this is e to the ln a times x. That's my outer derivative, times the derivative of the inside is ln a. So the outer derivative times the inner derivative. Okay, now I want to rewrite this e to the ln a, or whatever, ln ax. So using the same trick that we used before, when I have the log, okay, this is x is times it, I can bring x up into the exponent. Okay, so this is actually e to the ln of a to the x times ln of a. And remember, e and ln are inverses, so this is actually a to the x times ln of a. So this is why the derivative of a to the x is a to the x times ln a. Okay, so we just use the log rule so that we could write, we use the fact that the exponentials and the logs are inverses, so that we could write a general base in base e, which we hopefully believe the derivative of. Then we use the log rule to simplify it, okay, into something that we can differentiate with the chain rule. So then we took the derivative with the chain rule and then did all of our simplifying backwards, okay, and we see that it's itself times ln of a.